Okay, good morning again. I know there's a lot of people who are not here right now. Today is actually, we're still dealing with the second chapter of this class. So basically, which is chapter 22, okay? One of the things I'm gonna say up front right now about this chapter, and you probably have seen it already, okay? Gauss's law looks ugly, okay? At least at this point. It looks, there is a double integral on one side and there's a triple integral on the other side, and probably some of you guys did not do enough math already to handle this thing. So it looks kind of daunting, looks kind of formidable in the sense that somebody has to really do this multivariable integrations, and we're not ready for it. Again, the promise from Gauss's law is actually not to do those integrals, okay? The worst case scenario that you're going to be doing actually is a single variable integral. Today, and I know I mentioned that last time when we met, is we already have several examples for you guys. We're going to do example for 52. And I'm going to go with example 52 to some extent with a lot of detail in it, okay? And then also, I'm going to do 53 because I was debating which one of the two, 53 or 54 I do, and you will see why I like 53. 53, when I first saw it in my life, when I was taking this class, I was astonished, honestly. I thought this is the cleverest thing ever, okay? This method is useful for solving problems, whether, for example, the moment of inertia, whether the center of mass, whether in this case, the electric field, or that of the magnetic field down the road. So this method is actually common to all of these methods. And honestly, like I said, when I learned it, I thought this is the most clever thing I have learned in my life. Honestly. And until this point, when I go through these problems, I kind of enjoy them a lot because of this issue, okay? So I'm gonna do problem 53. Again, you guys have probably guessed I like data because that's how physicists work. So I'm looking at the book in here. So if you see me doing that, it's because the book is kind of heavy to put it in my lap anyway. So the other problem is problem 55, and those are from the 15th edition. If you have difficulty finding these problems, please let me know. There are some key concepts we didn't finish actually from the lecture that we need to go through. And so let me jump into your OneNote to make sure that we pick up from where we left off. And somebody already asked about the lab. The lab, we're not there yet in terms of the capacitance to do the next lab. So there will be a session this, hold on. Let me make sure I know exactly what I'm talking. Today is Tuesday. And the last time we had a session after class, which was, I think was good. I don't know if you guys enjoyed it or not, where we did the problems and we posted it. Is that the kind of things that you would think is useful or not?
Yeah, but Professor, I had a question.
Uh-huh.
You know how on the lab we went over the homework questions and how we would solve them? Well, I tried going back into the lab and it wasn't the PDF wasn't working for me. So I was gonna ask if you would upload the OneLook so we can reference it when we're doing our homework.
The OneNote itself, the actual file?
No, like the notes for that specific day.
Yeah, okay. I'm gonna think through this one a lot because honestly, I keep the video in there and I want you guys to actually go through the same steps as I was going, because if you see my notes, first of all, they're a mess and you probably have seen that already. And they are my own notes and they might not really help you because you're like, okay, the notes are there, so I'm going to look at them. I want you guys to go through the same reasoning. I want you guys, as a matter of fact, what I'd like to teach, I don't like to teach physics or math more than actually how you think about this process, how you actually go through the thinking. And that is actually the idea borrowed from Feynman and basically the great physicists who is basically instill in their students more the process than the actual result.
Oh, okay. Okay, that's okay. I was just having a problem getting the video to download. That's why I was having trouble to reference it.
Yeah, I would love for you to go through the same struggle as they did. This physicist and this great minds basically went through. and come up with a reasoning that convinces you that this is the way it's supposed to be, not otherwise. This is the end game at the end with you guys being in my classes, where you end up, hopefully. I know it's kind of sometimes is a little bit hard, but that's really what I want you to start thinking like they do. Because at the end, when the class is over, and you don't remember what is the electric field of the sphere again, or on a rod or something, you can Google it and you find the result in there. But if you are empowered with the way to think and solve problems, you can actually go through any new problem that you encounter in life and go through that process and hopefully have enough tools to resolve it. Does this make sense to you, Marcella?
Yeah, it does.
Yeah, that is really what I want to achieve with you guys in this class.
Okay, it's reasonable. And also, I was going to ask, so our chapter 22 homework on mastering physics is due on the 5th. Is that going to get extended because we haven't finished the chapter yet?
Yes. Please let me know, okay?
Yeah,
Please
because I
post.
was doing it. I was trying to do it, and like I was like, "What the heck is all of this?" And so I was gonna ask if.
Send me a reminder, Marcella. That's your job, okay?
Okay, I will.
Send me a reminder if you don't see it updated, because I was just checking in here quickly the comfort zone for this class quickly. So the lab is actually supposed to be this Thursday at 5 p.m. Okay. So if we don't finish stuff today, we're gonna leave it to then to do more problems. And hopefully more of you attend there too. And if not, at least watch and go through the same process, struggle through these things, understand them. Because if you don't pull your sleeves and do the actual thing and just rely on the notes in the book or my notes and something else, I don't think this is gonna work, honestly. I don't think it's gonna be useful for you at the end. You really have to sweat through these things. It's
I
not
already
like
am.
what?
I
You
already
are?
am.
Okay. No, actually, what do they say about, for example, I can watch tennis for hours and hours and hours, but I probably will never be able to do anything at it, because if I don't go outside and practice and practice and practice, and at the end become good at it. So that's basically the moral of the story in here. Good questions. Any other question?
Oh yes. The lab is due today, right? The first lab.
I think I'm gonna extend that one too, because we are still working on a few things in here. The first lab is kind of light in here for you guys, so you should be able to finish it today. Again, if you have difficulty with it, please let me know, okay?
Okay.
So I'm just looking at the notes in here. Were we ever able to find the electric field for all of these are problems? I'm looking at the lecture. Oh, here it is. I'm not looking at the wrong slide. Okay, so we did the, okay, let me share with you a screen first. Before that, I need to move it to this screen if I want to even write on it, because I have this weird stuff that doesn't work on the, okay. So this is chapter 22, the stuff that we did from last time, if you guys remember. And so we went through the law. This is how it looks like. Again, it's this, what I was referring to as being, looks kind of horrifying. Basically, it looks kind of scary, okay? But the promise of Gauss's law is actually not to do the actual thing. We did the rod. We found the electric field drops like 1 over distance, which is important. I mean, normally the electric field drops for a point particle drops like 1 over distance squared, whereas in this case, actually it drops only like 1 over distance, because there is more and more contributions from the rest of the rod. And that's what basically weakens, I mean, strengthens, to, if you wish, the electric field to some extent in that point. So it drops, but not as much as expected in 1 over distance squared. So that's basically the explanation for why that is. Again, this is a process through which of using Gauss's law so that it doesn't, you don't really do as much integration as you probably think that you might, okay? This, we did also the sphere. One of the important results we found for the sphere is, if I can ever find where my pen was, here it is, okay? Is that the electric field depends on how far you are. This sphere better be an insulator. And we're going to talk about what that means. Insulator, not a conductor. That's the material of it. So we need to understand what in the world is this two different things, conductor and insulator. Because if I take a charge in here, it's uniformly distributed everywhere. So that is what an insulator is. If it was a conductor, you will see soon, we can argue that the charge actually does not stay in the middle. It's going to move around. It's going to be actually toward the edge of the metal or the conductor in that case, okay? So this is something that we need to understand. So we have a charge in here, Q, was sprinkled throughout the entire material in here of this solid sphere. So the charge now distribution is uniform in this sphere. And we ended up with these two results that are kind of interesting. One of them is for R less than R, for R less than big R. I know the arrow in here is pointing to this one, and this is the result we found. So I can express it in terms of whether the density, this is applying Gauss's law again. So the electric field turned out to be, this is phi E, the flux is equal to the electric field times the surface area. So the surface area is this one, which is 4 pi r squared. And the charge enclosed, it's only enclosed in this volume, and that is the density times the volume of that sphere, which is 4 over 3 pi r cubed. Cancel the r cubed with the r, and this electric field grows linear with the how far we are inside the material. So if we are very close when r is 0, so the electric field is 0, and it starts to grow in strength until we reach the outside. As a matter of fact, if we draw this function, and let me rewrite it again for r less than r, use a black color. Again, r less than big R, what we found as the electric field is going, let me write it in terms of density, or all I have to do is change this row as just Q over V, and I get the expression with a big R, okay, and Q. But we can write it in terms of the charge density. It's 4 pi cancels the 4 pi, by the way, from here and there. So it'll be just rho pi R over 3 epsilon naught. Rho, I'm sorry, not pi, there is pi cancels also. Pi from both sides cancel. Divided by 3 epsilon naught. If you care about the vector, it's radial too. It's in the same direction as the vector R. So if you put the vector R and the electric field, by symmetry, again, we argue that it has to be radial because of the fact that if you close your eyes and take the sphere and spin it around one of its axes, it doesn't matter which, and I ask you, did anything change the sphere? You tell me no, because it looks the same to you, because it has this spherical symmetry. So whichever way you rotate the sphere, it's going to stay the same. Because the charge distribution is uniform, so the charge distribution will not change. So you say nothing changed to the sphere. Therefore, the electric field also need not to change, at least on that point where you are looking at it. For that to happen, the electric field must be radial. It cannot be pointed one way or the other, because if I rotate the sphere one way or the other, you're going to see that the electric field now is pointing in a different direction than it was before, if I rotate it just enough. Now, to retain that symmetry, then the electric field must be radial. And that's the argument of the symmetry in here. Okay, so you really need to make those arguments of symmetry. Furthermore, the electric field needs to be the same as long as I am on the same distance, r. Okay, if I change r, of course, the electric field might change and should change. But if I am on the same sphere, the electric field needs to retain its value, because again, if I tell you close your eyes and I do something to the sphere, rotate it one way or the other, and I ask you, did anything change to the sphere? You tell me no, the charge distribution is the same. Therefore, the result of that need not to change, namely the electric field, which is produced by this charge, should not change because the charge distribution did not change. And the only way for that to happen is that as long as I'm on the same distance, the electric field is the same. Because if you argue that the electric field on one side of the sphere is different than the other side of the sphere, all I have to do is just spin it one way, and all of a sudden, what you thought the electric field is 10 newtons in here per coulomb now has shifted to the other place, and you'd see the electric field changed magnitude, whereas the sphere did not. As far as you're concerned, when you close your eyes, I rotated it, so nothing happened to the sphere. Therefore, the 10 Newton need to be everywhere on the sphere, 10 Newton per coulomb, as long as I am on that distance from it. You guys understand the argument of symmetry? It's a very powerful argument, okay? So the electric field is radial inside. Outside, though, it looks like a point charge. So outside, it's this expression, R greater than big R. We found the electric field, again, if I want to put the 1 over 4 pi epsilon naught times 1 over distance squared times the unit vector r hat. So this is the radial vector again. Normally, and sometimes you will find this writing, okay, so be careful with it, okay? R hat times the length of the vector r is the vector r itself. Because the vector, it's a magnitude times direction, any vector. The vector A is the same vector as the magnitude of A times wherever it's pointing. That's what the I hat means in this, A hat means in this case, is the direction of that vector. So sometimes this R hat is written as the ratio of the vector itself by its length. Obviously, this has unit length, which satisfies the condition for a unit vector. Because unit vector has one length of 1 unit. And the direction is the same as that of the other one. This indicates that it's radial. Sometimes this very same, of course, times Q in here. I'm sorry, I forgot the Q. Q over 4 pi epsilon naught times R itself divided by R cubed. You might be tempted when you see this expression to say, this, oh, the drops like 1 over distance cubed. No, it still drops like 1 over distance squared because of the fact you still have a distance also in the numerator in here. So there is a distance, there is a meter and meter cubed, it's still 1 over meter squared. Okay, so sometimes this unit vector, which has a length of 1, can be written in this format. So don't be confused with this thing. It's still the same stuff. Okay, and this looks awfully similar to that of a point charge, because a point charge that has no size whatsoever has an electric field. This is a point charge. This is where we started from, by the way, has Q over 4 pi epsilon naught times the same stuff. R hat over R squared, or R over R cubed, if you like. R vector over R cubed. So this looks similar, as if the entire sphere is just a point particle that is located at its center, as if the entire sphere is actually located in here as just another charge Q. That's it. Oh man, charge Q. Okay, and we're measuring the electric field somewhere away from it at the distance R. Okay. It's the same argument. And this is basically what Mr. Newton argued at the end, that the apple, you put it in here a meter away from the Earth and you measure its weight using his formula, as if taking the entire Earth and put it in its center and using the mass of the Earth instead in his famous formula, which is G times M of the apple times mass of the Earth divided by the distance squared. It's the same thing. With the distance in here is not just the meter that you take the apple from, but it's rather the entire distance, which is a big radius of the Earth, 3,600 kilometers. So this is the same argument in there. Okay, so if I draw this one for the function of how the electric field depends on the distance from the center of the sphere. So this is E. So it's some value in here. I can actually find this value in here at the radius, first of all. This is the radius of the sphere, R. It's going to grow linearly. As you can clearly see, it depends on R in here, in magnitude, okay? It's only on R, proportional to R inside. So when R cubed cancels the R squared, you'll be left with an R. So it's going to grow linearly in here, up until a certain point in here. At that point, it's going to drop like 1 over distance squared here, okay? So if you're curious trying to find what this value here immediately at the surface, you plug into either of the expressions and the function is actually a continuous function. Because in here, if you plug R equals to big R, this value is actually equal to Q over 4 pi epsilon naught times 1 over R squared. And if I plug in the value of R, Q being basically just the volume times rho, the volume has a 4 pi over 3 cubed, and the 4 pi cancels the 4 pi, but I still have 3 in the denominator, and epsilon naught to stay there. And I have an R cubed in here, cancels that R, but of course I have to change this one by R. So the two values actually match in here. So this 2 is where the maximum electric field. So the electric field grows linear up to a certain maximum value, and then it starts to drop like 1 over distance squared immediately outside of the sphere. So this is how E depends on distance for a solid, non-conducting, or what did I call it? insulating sphere with distance, okay? Let's get this stuff of insulating and non-insulating stuff out of the way, okay? Conductors and versus insulators out of the way, okay? So we have two key concepts in here. Conductor and an insulator. I know there are more stuff that you guys probably heard of, semiconductors, for example, which probably we're going to discuss down the road, maybe at least in the lab. And also superconductors, we're probably going to mention them briefly, but we're not going to do much with them. We'll leave that when you guys get into solid state physics or material science or something like that, depending on where you're going to end up with. So what's the difference between the two? If I take a conducting material, let's say, for example, I have atoms in here. I'm going to draw 3, 4, 5, 6 atoms. And I have 5, 6 atoms also in here for this guy, okay? Both of them have atoms. Each atom has its own electrons. So this one has an electron. I'm going to just take valence of 1 so that there is only 1 electron per atom. Same thing as in here. Okay. This is the outer shell, basically, for the atom, if you ever take chemistry. Now, in the case of this metal, this material, the electrons belong to their respective ions or atoms. They're strongly bound to them. You cannot yank it out of the atom easily. Same thing with this guy, same thing with this guy, same thing with this guy, same thing with this one. So if you apply an electric field inside this one, nothing happens. Okay, at least a normal electric field, nothing happens. Because these electrons cannot be yanked. Yes, they will be experiencing F equals to QE, and since this charge is negative, so this is the force that they're going to be experiencing, but that's fine, okay? They're not going to be moving because this force is not big enough to yank them out of their atoms, okay? Unless the case where there is tremendous electric field where this happens, a discharge actually will happen in materials like this ones. You guys know what that kind of discharge has, at least on a daily experience? Do you guys experience that? There is tremendous electric field that builds up over time so that you see actually discharge before your eyes.
Would that be lightning or static electricity?
Is that static electricity?
Exactly, because air is an insulator. Gonzalo, were you saying something?
I was going to say static electricity.
Yeah, actually, you have to build tremendous current for that to, tremendous voltage for that to happen. You're right. I mean, when you are walking, actually, that is actually the same thing. When you try to remove something, that is actually also discharge. I mean, you're walking on the surface with probably the right shoes and everything, and there is a buildup of static, and somebody tries to shake your hand, and you see actually a spark. And this spark, because of the fact that the electric field between where the contact is going to happen is so high that actually the charges will move and you see them before your eyes, okay? So the air is an insulator. Normal air is an insulator, okay? But because of the clouds that are rubbing against one another, they build up tremendous electric field basically between the lower end of the clouds and the upper end of the clouds. Lightning actually happens between the inside the atmosphere itself, but also happens between the ground and the earth too, when there is tremendous voltage basically and current that builds up over time. I mean, electric field that builds up because of this phenomenon, and you actually see it outside. You see it through the lightning. So that's basically the point in here. So that is a discharge actually, and that happens too. So an insulator can do that. But it's much easier actually with a conductor. You don't need that much electric field. So if you apply the same electric field of a conductor, these electrons, they start moving right away. Okay? Because they experience this force, because these electrons, they're actually not strongly, if you wish, committed to their own atoms. Okay? Okay? The minute they see an electric field, this electrons actually, electrons belong to the community of atoms, not to a specific atom, So they can move at will in a conductor. That's why you have conductivity. That's why you have electricity. That's why you put a wire, for example, of copper, for example, and you apply an electric field on both ends in it, and all of a sudden the charges starts to move in one direction. The current, because the charges that are moving are actually electrons, they have negative charge. You will see current, a galvanometer, for example, or an ammeter move in this direction, showing you that there is a current I flowing through this one. We'll get into this one in more detail. As long as you have a battery in here, the minute an electron falls in here, it takes it basically and drag it and put it in here. So it's going to fly again, and so on and so forth. So that's what the role of the battery is, if you're curious, okay? Or the plug in your wall, okay? That's exactly what the role is. The minute the electron leaves the copper wire, or doesn't matter, as long as you have a metal in here, which is a conductor, as long as you have a conductor in here, it's going to drag it and take it to the other end and push it back again. And then the electric field is the one that is doing that pushing, and the current will be in the opposite direction. So that is basically what the conductor is. Conductor, because of this property, has a problem. Let me explain what that problem is. You cannot sprinkle charges and expect them to stay where they are, because they start moving. Okay. Let's say, for example, a single charge appeared in here, a positive charge appeared in here, because an electron decided to leave that atom for some reason. Okay. Now, this atom next to it that is neutral will replace it for it. Okay. Now, this positive charge now becomes neutralized, and the positive charge will, in fact, has moved to this side. Okay. The negative charge that left this one is probably somewhere in here, because it cannot stay in here too. It's going to be pushed all the way here. The point here is just follow this one. You will see what happened. Now, this atom that is next to it will see that this one now is positively charged, will move its electron in there, because that's not it, actually. It belongs to the community of the electrons, of the atoms. So now this becomes positively charged, and this is neutralized now. Okay. The same hopping actually happened for the negative charge that ended up toward the end. And then at the end, this is basically all of this positive charge happened to it at the end is going to stay in here, because there is no neighbor in here where it can borrow charges from. So at the end, the charges cannot stay inside the bulk of the conductor. So Q is equal to 0 inside the conductor. Okay, the net charge must be 0 no matter which way you do it. So if you try to sprinkle a negative charge in here, same thing will happen to it, because it's going to be staying as an extra charge in here. It's going to hop until it reaches the end, and then negative charges will be sprinkled in here. So the reason why I put a positive in here is because somehow I thought that this was neutralized, and I yanked an electron off of it to keep it positive. But if I just take a positive charge, an ion, for example, put it in there, they will see it basically without an electron, and they will move their electrons just enough. And at the end, until that positive charge stays toward the end, to the outside, and cannot go anywhere unless a discharge happen, okay, through this insulating material in here. And if there is no insulating material, there is no way you're going to borrow anything from outside. This is actually equal to the work function that is probably something that is probably going to be explored down the road when you guys do physics 4D, okay? That is basically the power with which that at the end. So at the end, basically, there is no charge inside a conductor. Whereas it's possible to do the same thing in here, because you come in here, for example, and you put a positive charge in here by, for example, having an ion in here. So this is positive. It cannot take anything from anybody, because all of the other charges belong to their own things in here. Is the internet has a problem or what? Guys, can you hear me?
Yeah, I can hear you.
Yeah.
You're perfect.
You
Okay,
have a
very
little
good.
glitch.
Yeah, you're clear.
Okay, so as long as if it's inside an insulator, that charge will stay there. There is no problem. It cannot go to the surface. I mean, you put it there, it stays there. You take it and put it inside somewhere else, it's going to stay there somewhere else, okay? As a matter of fact, if these are additional charges, they probably would have another one in here, so they will experience forces among themselves, but that's fine, okay? So we need to balance this thing somehow, but that's the end of it, okay? These charges cannot borrow anything from anybody, because they belong to their atoms. And that's the usefulness of an insulator, actually. That's why the air is good, Because if there is a charge sitting in here, it does not come to you and harm you or leave from your body, go somewhere else, because the air is actually an insulator. Wood is actually an insulator. Metals, on the other hand, are all conductors because of these properties in here. Their electrons don't belong to anybody. So what is the electric field inside a conductor? Let's take this conductor, for example. So this is a conductor. I'm going to plunge it inside an electric field. So there is an electric field pointing in here. Okay. Well, it is a problem now. So this is what's going to happen. The electrons will be subject to this force. So if I have a negative charge in here, they will be subject to this force. And they will move actually until they reach the edge. Okay. Where are they going to come from? They cannot come from the middle anyway, because if they come from the middle, another one will replace them until we reach the other side, where they will deplete this side correspondingly. You guys see that? And they will create their own electric field to balance the external electric field. So if somehow you make up, for example, 10 Newton per Coulomb in here, they will make up, pointing this way, they will make up their own 10 Newton per Coulomb in doing this motion to cancel that one. That is the only time they stop. Otherwise, as long as there is more electric field, they keep on moving, migrating. If you weaken this value, let's say, for example, I bring it down to 8 Newton per Coulomb, they will move some of them back to where they were just to bring this number down to 8 Newton per Coulomb to cancel it, that's all. Let's see why the electric field is equal to 0 inside the bulk in here. The net electric field equal to 0. We're going to apply Gauss's law for that. So what I'm going to say in here, take any arbitrary surface. It doesn't matter which. I'm taking this arbitrary surface. I'm going to say in this case, the flux of the electric field surface over this area in here, which is, I'm going to call it big S, okay, over closed surface S, must be equal to the charge enclosed. I just argued that you can never have charges enclosed inside the bulk of a matter, no matter which way you do it, because they will move around, they shuffle themselves around so that they neutralize everything until they reach the edge, in which case they cannot, because they cannot borrow charges from the outside. Okay, so in this case, the charge can only be on the surface. So that is actually the property of a conductor. So conductors can have charges only on their surface. So you cannot have a charge inside the conductor. Because of that, the charge enclosed in the surface is 0 divided by epsilon naught. So 0 divided by epsilon, that's 0. That means the flux of the electric field through any arbitrary surface S. So S is arbitrary, actually. Arbitrary inside the conductor. Outside it may be finite, okay? We don't care about outside. We just want the flux of the electric field inside. And that has to be 0 because of this argument that I'm making. Because of that, the area is arbitrary. It's like taking the integral of a function over several different, whichever shape you're going to take it, you're going to find 0. The only way that this is true, and this is calculus basically, is that this electric field is 0. If you care about the vector, it's the vector 0. There is no electric field inside the conductor, no matter which way you do it. That's why when you apply an external electric field, the charges will move just enough and create their own electric field to cancel that electric field, at least inside. You guys understand that? As long as there is a net electric field, charges will move. You can play a game with this conductor, actually. You can, the minute the charges move, you can actually reverse the polarity of the electric field and see what happened. Well, they move back in this case to cancel the new electric field that's pointing in the different direction. So you keep on changing and the charges will move back and forth because they don't belong to nobody. That's their problem. They can run at will in a conductor, okay? They're loosely connected, if you wish, to their atoms in the case of iron, which is really a poor conductor, but it's still a conductor nonetheless. Versus, for example, for copper, which is much better conductor, where the electrons have much more mobility than that of a iron, but they do that too. So you can drive them crazy, actually. If you can switch fast enough, you're going to see them flying basically back and forth. And that is a so-called plasma frequency in this case. Actually, you will see smoke, okay, fire. So that's basically the difference between a conductor and an insulator. Does this make sense to you guys? At least the interpretation of these things?
Yes.
Okay, remember the fact that inside the conductor, the electric field is zero, no matter how you do it. Okay, that's why I was making a big fuss over the fact that this sphere better be an insulator, because if it's a conducting sphere, the electric field, this result we found will be zero. So the only reason why we ended up with a non-zero value is because I'm making the assumption that this is an insulating sphere. So I made in here an emphasis on it so that you guys know that. And we'll be dealing with conductors and insulators in this class. So that's why it's important to understand that, okay? Before we take actually any problem and do them, let me actually do another important result, and that is for a plane, an infinite plane. So we did the, let's take stock of what we did so far using Gauss's law. We take an infinite line, infinite rod, okay, and we found that the electric field basically drops like 1 over distance. So if you're curious, it's lambda over 2 pi epsilon naught times the distance y from it, okay? We took so this is a 1D, one-dimensional object. We took a 3D object, which is a solid sphere, and make sure that's an insulating sphere. It doesn't matter, even if it's a conducting sphere, if you are outside, you're going to find the same result, okay? It's going to be q over 4 pi epsilon naught times 1 over distance q squared, okay? 1 over distance squared, not the radius, 1 over this distance squared, okay? So that we found it outside of the sphere. Inside the sphere, turns out if it's an insulating, it's actually it's proportional to the distance. So those are the results that we found so far. We're going to take another case in here that is going to be tremendously important for the next chapter, which is actually the capacitor, okay? Which is preparation for our stuff in there. And that is actually a two-dimensional object. Two-dimensional object, what I mean by it is a sphere, a plane, infinite plane, infinite plane. When I say an infinite plane, it doesn't have really physical size. So it could be a conducting plate, or it could be an insulating plate, as long as you have a uniform charge distribution, because it has no depth in here. So it's all of it is really a surface. So if it's a conducting conducting plate, it's fine. Plane or plate, okay? Could be conducting or, okay? As long as it's an infinite in size, huge in size. You say infinite doesn't exist in physics. It exists as long as you are not too far from it. We're going to come to a point in here at a distance, I'm going to call it y, similar to the rod. And I'm interested in trying to find the electric field in that point. So what is E here? That is the question, produced basically this one. Of course, I took a charge Q and sprinkled throughout this entire surface so that Q over A, so the surface in here, of surface size A, it's a big area A compared to this distance y. So here, that's what I mean by infinite in here. So infinite in this case is relative in physics. Okay. So what I mean by it is that this distance y is much, much lesser than the square root of A, which is basically the size of this A, its length or its width, okay? So this distribution is uniform, and since it's an area distribution over an area, we're going to use the symbol sigma in here. And sigma in this case refers to the amount of charge per unit area. Per unit area. So basically, the units for sigma are Coulomb per square meter. In this case, if you guys remember, we used rho. Rho was Q over V. And Q over V in this case was assumed to be uniform, and the units for rho turn out to be Coulomb per cubic meter. In this case, we use the symbol lambda, which is Q over the length L. Obviously, the same situation we encountered here, we were talking about length. being infinite, well, what I meant by it, it's much, much bigger than y. That's what we mean by an infinite also in this case. So in this case also, it's still relative. And the units for lambda are actually coulomb per meter. So this is a linear distribution. This is a volume distribution. And this is an area distribution. Okay. Surface distribution of charge. As long as I know that, then we're in business, okay? And this distribution is uniform. That means the same amount of charge exists everywhere per unit area. I'm assuming it's positive, okay? If it's negative, the direction of the electric field will point in the opposite direction, no more, no less. So I'm assuming that this distribution is somehow uniform. We're in business. Let's try to use Gauss's law. I'm going to use the symmetry argument again in this case. Before I do that, yeah, let's see what kind of symmetry in this case. Let's talk about symmetry. If I take this infinite plane and move it up and down while you're not looking, of course, you're not going to see any change in the distribution. The plane would look the same, doesn't it? If I move it up and down, because it's infinite, it doesn't matter. You guys see that? Yes or no?
Yes.
Okay. Again, if I spin it one way or the other, it doesn't matter. It's infinite, okay, compared to this size. So expect the electric field to be pointing for the argument of symmetry in this direction. And let me tell you why. Because if you somehow argue that it's pointing this way, okay, all I have to do is spin it just enough, and then the electric field will spin with it. So I ask you, did anything change to the distribution of charge? You say, no, it looks the same after you open your eyes. But why in the world the electric field has changed direction then? Oh, that means that direction I took is not right, okay? So as a matter of fact, any direction you take is not going to work. The only direction that is going to retain that symmetry is that one. That is one point. The second point, if I took an area now, okay, I'm going to call this area A prime because I already called that area A, of this shape. So I'm trying to project this shape in here on the sphere. So this is the area I'm talking about in here, a distance y from my sphere, from my plane. I'm going to say the electric field is the same everywhere as long as I am on that distance. It's the same magnitude. So if this is 10 Newton per Coulomb, everywhere it's 10 Newton per Coulomb. Because you could say, you know what, I don't like this analysis. I think the electric field is actually 5 here. It may be 10 there, I don't care about it, but this is actually 5 Newton per Coulomb, and it's different than everybody else. I'll tell you, hold on, close your eyes. I'm going to move the electric field slightly enough so that this point now comes in here. So now I ask you what happened to your 5 in there. It has changed places. Or the one that was 10 that was different than the 5, I can move it upward, and your 5 now becomes a 10. You ask you, did anything change to the charge distribution? And you say, no, the charge distribution looks the same because it's an infinite plane when you open your eyes. Why then the value of the electric field has changed from what you thought it was to this new value? So the electric field must be the same everywhere. If it's 10 somewhere, as long as we are a distance y from it, it has to stay the same as long as we are on that surface. Does this make sense to you guys? The symmetry arguments?
Yeah.
Okay, so the electric field is the same on the surface A prime, and whatever value it is, it's this blue value. And it's pointing this way. So I'm going to choose my Gaussian surface now. I'm going to choose this surface as my Gaussian surface. Arbitrary area A prime. So the answer should not depend on A prime. I'm going to extend this surface to a distance y on the other side. So it's y on this side and y on the other side too. Okay. Hopefully you guys can visualize this surface with me. So this is the same area A prime, by the way, as on the other side. Yes. So far, so good. So the red one is my Gaussian surface. This is the outer surface. This is the, I'm not looking at the volume. It looks like it's a volume, but I don't care about the volume. I care about the actual surface, the skin, if you wish, of the potato. I don't care about the meat of the potato. Okay. Yes. So this is, the red one is the Gaussian surface. And it's a made up surface with this parameter A prime that is kind of annoying. So the answer should not depend on it. This lateral surface in here will have the following situation. The area of the lateral surface points this way. So this is the lateral area. And I just argued that the electric field needs to point away from it. Always points away from the plane, actually. So the lateral area and the electric field in this point are perpendicular. So in this case, there is no contribution if I do the Gaussian surface, the integration from here for the first part, which is the flux of the electric field in here. The flux of the electric field on this side over the entire enclosed surface. That's why I have to worry about the lateral surfaces, because I want the entire enclosed surface, the Gaussian surface. So I will have 0 from the lateral surface. So this is, let me rewrite Gauss's law first of all. It says find it for the entire Gaussian surface. The flux of the electric field, basically EDA, plus is equal to the charge enclosed divided by epsilon naught. Now, the flux in here encloses the lateral surface and the two surfaces, A prime on one side and A prime on the other side. I just argued that the electric field is the same on this surface and the area is pointing in here. So the dot product of these two involves a cosine of 0, which is 1. This area in here, for the same reason, because this is a surface, so it doesn't matter which way I look at it, it's a positive charge. So the electric field also must be pointing in here too. And it's the same magnitude because I'm in the same distance y. That's why I chose that y, okay? That's why I chose this Gaussian surface. So this, the electric field in here in magnitude is equal to that electric field in magnitude. Okay, but it's pointing in the wrong direction though, because I'm on the other side of the plane. It needs to point away from the plane in any direction I am at. The area A prime also points in the same direction. So that dot product also involves a cosine of 0 degrees. So there is the same contribution because the areas A prime are the same and the magnetic, the electric field is the same. So this 2 will have 2 of them. And because the electric field is the same everywhere in here, so I'm going to take it out of the integral, and all I'm doing is multiply by the area, because when I sum through the area, I'm going to get the area, which is exactly A prime. So from the two frontal surfaces, and there are 2 of them, by the way, plus the lateral surface. The lateral surface is going to give me 0 because E and A are perpendicular. I don't mean that A, I mean the area in this case. The lateral area are perpendicular. In this case, they are parallel, so it's going to give me 2. I'm going to take any of them, it doesn't matter. The electric field is the same throughout that area times the area itself, which is A prime. So 0 plus this number must be equal to the charge enclosed. Now I need to worry about the charge enclosed. The charge enclosed is this much charge only. So let me use a different color in here for the charge enclosed. So this is the charge enclosed in this case. And it's the same area A prime times the charge distribution. I have sigma charge per unit area, but I took an A prime in here. That is the only charge enclosed. Don't count the one outside of this area, only the charge enclosed. So this is going to be sigma times A prime, I'm sorry, divided by epsilon naught. Charge enclosed divided by epsilon naught. That's Gauss's law. You see the symmetry arguments in here? We didn't do actually any integration. All we did was just basically argue our way, one way or the other, to find the direction, argue one way or the other to find the magnitude. Once we do that, then we plug it into Gauss's law. So that what looked like daunting tasks to do, those integrations, we boiled down to basically multiplying and doing simple algebra. Obviously, I'm interested in trying to find the electric field from this expression. So let me change the color in here quickly. So what I ended up with is 2EA prime is equal to sigma A prime over epsilon naught. And that's good because we don't want A prime to be part of the answer at all because it's a made up surface. It's a fictitious surface. It's not a real one. Gaussian surface is a made up surface. That's why its properties should not matter. So the fact that we invented a Gaussian surface of this property, one of its properties is this one. The y is an intrinsic property of the surface also that is coming from the lateral surface, but that's part of the problem. So the answer may depend on y, okay? But not on A prime, because A prime we choose it arbitrarily, just the size of this surface so that we can do the math in here. So again, the answer should not depend on what you invent as not part of the physical problem. But this is good. So that is actually good. And that means the electric field does not depend on A prime. But one surprising factor in here, and this result is very important, by the way, for capacitors later on. We will need it for capacitor, needed for capacitors. So you need to remember this result, okay? So the electric field is equal to sigma over 2 epsilon naught in this case. And it doesn't depend on y, independent of y. And that is kind of a surprise because we believe the electric field should depend on how far we are from the plane. If we are closer, we expect the electric field somehow to be stronger. If we are far away, the electric field should be weaker. But this result doesn't suggest that at all. It doesn't matter how far you are. You could be a mile away from the surface and the electric field is going to stay the same. As long as the surface is bigger enough than that, at least its physical size is bigger than a mile, it's going to stay the same. Why, you ask? Well, if you move away, just like when we argued for the rod, and it diminished a little bit of the strength of the, how far the electric field would diminish with distance, it's the same thing, except now we have two dimensions that are contributing to the factor. And the net effect is whatever increase in the magnetic and the electric field as you get closer and closer to the charge, to the surface, you're going to be compensated by less and less contributions from the rest of the rod. Or as you get further and further away, you're expected to diminish, but it's actually contribution from further and further parts of the rod because it's an infinite. And plane because it's an infinite, similar to the argument with the rod. Except in the rod, we had only one-dimensional problem in this case, which was infinite. So the effects were only canceled one of the dimensions in this case. So instead of 1 over distance squared, we ended up with 1 over distance. In this case, the plane is two-dimensional, and the contribution of canceling of 1 over distance squared was just enough to cancel the 2 distance squared, and the electric field turned out to be a constant number. Constant. That's a key word in here. You know how you do, guys, when you're writing everything in caps, an email to email to somebody or a text message or something. What does that supposed to mean when you write everything in caps? Marcellus, are you saying something in here or somebody? And you put an exclamation, and like you do our former president, you put 17 exclamations next to it.
It's very important.
But what does it mean when you send a text message to somebody, everything in caps?
I'd say you're yelling at them at that point with all caps.
That's what I'm trying to do in here. I'm trying to scream at you guys. Is this loud enough?
Yes.
Pretty loud.
Remember this result. It's very, very important, okay? This is a very, very important result for the electric field for the plane because it's going to have immediate implications for our capacitance later on down the road, okay? So that is why this result is important, okay? So again, we didn't imagine if we really have to do chapter 21 in here, and it is doable actually. You're going to take an element of surface in here, it doesn't matter where, and you're going to do an integration, and it's going to be a nasty integral involving 2 variables in here, and it's going to end up with the same result as we do, okay? Actually, you're going to do some cancellations left and right, but you're going to end up with a complicated result that doesn't depend on how far you are. It comes out exactly like this number. But it's a lengthy calculation, actually. It's going to be probably maybe a page or 2 pages long to get into the same result. But Gauss's law makes it I mean, the only inconvenience of the Gauss's law, if you wish, or the difficulty with Gauss's law is recognizing the symmetry and argue one way or the other with the symmetry, okay? So I think we have enough theory for this class right now, unless you guys have any other question to delve into a problem, and we still have good time. I mean, we still have over half an hour, or about half an hour, because I thought we end at noon. Still have about half an hour. Any questions before we get into problem 52? And it's a long problem, by the way.
Oh, Professor, yes, I do have a question. So,
Yeah.
you remember how we have our discussion boards and we had our introductory one?
Yeah.
On the submission, we were supposed to submit it through the section in the module, right?
Yeah, you submitted there in the discussion itself.
Okay, because the discussion, like when you have discussion, chapter 21, those were the Zoom and the labs. So we weren't supposed to reply there. We were supposed to reply in the actual section, right?
You're supposed to reply where the discussion for each chapter has its own discussion session for the chapters, okay? Each discussion session has its own assignment that's attached to it. Today's assignment is to finish the calculations and convince yourself that the calculations we're doing is actually correct for this problem.
So for
So
this
you will
problem,
have, hold on, you will have after this session, I will go and download the video and basically put it on the discussion session. For those who are not live with us, they will watch the video there too and see the assignment for today and basically answer the prompt there and there where the video for the session is. It's going to be in the discussion for chapter 22, part 2.
oh, okay. Because I thought that we weren't supposed to reply to that. I thought that was just for the people that had like didn't watch the live and weren't participating.
No. It's still everybody, okay? Because I don't take attendance. That's the only way for me to make sure you're doing the work they're supposed to be doing.
Oh, okay. Okay, thank you, Professor.
Okay, no problem. Okay, so I know we're going through a transition. You guys are not used to my system and used to somebody else's ways of doing things. So that's why there is a leeway at the in the beginning, but I'm hoping that you guys will pick up the habits down the road and do these things. Because as I was saying in the beginning, physics is not really a spectator sport. So you really have to do these things. If you don't do them, you're not gonna be able to learn anything, okay? So, even if we were in class, honestly, this is my method. Even if we are in class, in session, that is, I mean, face to face, I do ask my students to do participation, and I grade it actually for participation, and they actually do assignments in class. And those who do not come to class and they go somewhere else and everything, they lose on participation. I used to wait a little differently, but now online there is more emphasis on it than actually face to face, because in face to face I can see your eyes and I can see where you stand and you can see me and I can really tell whether or not we need to go more about it, or when I incite you, we go there and basically do it. But now online, basically, unfortunately, this is probably true. Some of the people basically they turn on and they probably will go and continue with their phone and things like that. And that's not going to be helpful to them, especially when it comes to physics. That's why I really make a big fuss over this thing. Okay, hopefully you guys also find the benefit from it too while you're doing this. Okay. So, problem 52. Problem 52 and problem 47 and problem 61 from this book. They're typical problems, excuse me, that a lot of times I used to test on them. So there is no telling probably for you guys whether or not you're going to be tested on them or not. So again, you need to really pay attention to these kind of problems, okay? Ever since we were ever since we discussed these discharge distributions, we were dealing with a word that we used extensively, and that is the word uniform. Okay, the first word that you read from this problem, problem 52, is a non-uniform. So it's not what we've been doing so far. This is not uniform. This is distribution that is not the same. Problem 47, the first word is a non-uniform, again, not uniform. Problem 62 does not start with this word, but it's going to get into it very soon, okay? A region in space contains positive charge Q distributed spherically such that the volume charge density is given by, and it gives you the charge density, which is not constant, basically. That's what uniform is. So this problem, this is not true. We're dealing with a non-uniform charge distribution. That means rho is not constant. Okay? So from the get-go. So that integration on the other side will just multiply, plug in rho times the volume divided by epsilon naught is not going to work. So we really have to do some honest work then now. Okay? So problem 52 now, and this is true for the magnetic field down the road too, by the way. When we do that too, you will have current densities that are, we're going to do the entire lecture uniform, and then when we're doing actually some of the problems will be we will have currents that are non-uniform distribution of currents. So in this case, they give you rho, and they tell you rho specifically is a function of distance, and it's equal to rho naught times 1 minus 4r over 3 big R. This is when R is less than or equal to big R. But when R is greater than or equal to R, the charge distribution is 0. Okay. So let's plot this function and see how it looks like. Rho naught is constant. So this number is constant. And this R is actually the radius of the sphere. Okay. So if I plot this function as a function of the distance, this is how this function look like. This is R. This is big R, radius of the sphere. And here, I know the charge is equal to 0. So there is no charge in here. Okay. And for R equal to 0, this is equal to rho naught. So this is rho naught. Okay. And for R equals to big R, R over R is 1. And then you have 1 minus 4 over 3, that is negative 1/3. Actually, 3 minus 4, that's 1 divided by negative 1, that is, divided by 3, that's negative 1/3. So as a matter of fact, in here, the charge is negative R naught over 3, okay? And it's a continuous line, as you can clearly see. This is linear in R. So it's positive in this region, and then it vanishes at some point, and it's going to change sign and becomes negative. So it's negative in this region, and then it drops to 0. So this is how the charge look like. At some point, this charge cancels, and I can find actually the point where this cancels by just equating this to 0. So all I can do is I find 1 minus 4 over 3 R over R equals to 0. And this is clearly true if I do this algebra correctly, that R is equal to 3/4 of an R. So 3/4 of the way, the charge drops to 0. Okay, do you guys see that? And then it changes. So this is how the sphere look like if I want to envision it, okay? So there is a sphere, not a circle, a sphere, okay? Somewhere in the middle, and all the way to 3/4 of the way, the charge is positive. And it starts with a big value, rho naught, and it starts to go down linearly. So as I move further away, as the charge distribution starts to be basically spaced apart, okay? 3/4 of the way, the charge vanishes. And then it's going to appear again as negative charge. Initially small values. And then they become denser and denser as I get near the surface of the sphere. Okay, so this is not uniform. Do you guys see that? As a matter of fact, it's positive one side and it's negative to the other side. Outside, the charge is 0 because this is the shape. There is no charge outside of the sphere. You guys, can you see the somehow this math in here, how it's translated to a charge distribution inside the sphere? Yes or no?
Yeah.
Okay, so all I have to do now is try to answer these questions. The first question is, find the total charge contained in the charge distribution. So we need to find the total charge Q inside the sphere. Obviously, this sphere better be an insulating sphere, otherwise this is not going to work. Okay, so it's going to be the integral over the volume of this charge distribution. Remember, the charge is rho, so rho dV, but rho is not constant. Now, rho is a function that depends on how far we are. As a matter of fact, it's non-zero between 0 and big R, and it's 0 anywhere else. And between 0 and R, it's equal to rho times 1 minus 4/3 R over R times the element of volume. Here is what I'm going to do in here for the element of volume. I'm going to take a sphere in here. This is not, again, a circle, but rather a sphere of radius R anywhere. And I know the area of a sphere, which is 4 pi R squared. And I'm going to move a distance dr from it because I'm summing through this one. And the volume enclosed in this case is going to be just the area times the volume, okay? The area times the height. The area is of the sphere is 4 pi R squared, and the height is dr. So this is the element of volume dV, okay? If you're not convinced, just look at the volume of a sphere, which is 4 pi R cubed, and take its differential form, which is derivative with respect to R, and you're going to find it's 4 pi R squared dr, because the cube and the 3 cancel. Do you guys see this? The element of volume being this expression or not? Yes or no? If I take a sphere, I know its radius, I'm sorry, it's a sphere of radius R, of course. I know its area is 4 pi R squared. If I move slightly above it by distance dr, I'm containing now a volume that is equal to the area times the height, and the height in this case is dr. Can you see that or not? This is the element of volume for a sphere. Byron, are you saying something?
Oh, yeah, I was just saying that now. Yeah, it makes sense.
Okay, element of volume in spherical symmetry. When you have a spherical symmetry, okay, spherical symmetry. If you don't have spherical symmetry, you really have to involve d theta and d phi, and the problem becomes very complicated, okay? But if you care to include them, you do. And at the end, you're going to have, this is the element of volume in polar coordinates, by the way. It's going to be what? R squared sine theta, dr, d theta, d phi. So when you integrate over d theta and d phi, you're going to pick up 4 pi. So you'll be left with 4 pi R squared dr, exactly how we have it, okay? So this is in general. So if you ever took this calculus stuff in there, this is the element of volume in polar coordinates, okay? In space, of course, not in 2D, okay? So that's the thing about it, okay? In either case, this is basically how it is. Just take an area of a sphere, flatten it, and go height dr from it, and it's going to be the area times the height, and that is the volume, okay? Since now we know the area is this much of a sphere, which is 4 pi R squared. And if I go distance dr from it, this distance is dr. That is the volume enclosed in this element of volume, okay? Area, which is 4 pi R squared, times the element of volume, okay? Times the height, that is going to give me the volume in this case, okay? So, any questions? I mean, hopefully you guys, because this is critical. This step is critical for a lot of the spherical symmetry problems. This is where I see a lot of my students actually miss the point when they're trying to find the calculation in here. Does this make sense to you guys? I know Byron agrees.
Yeah, it makes perfect sense.
Okay, so now I have to multiply by the element of volume, which is 4 pi R squared dr. That gives me now the charge enclosed. We're in business now. So all I have to do is pull this constant out of the way and do a change of variable, which is typical in this case. So I'm going to call R over R as being the variable u. That means dr is simply equal to R du. Okay, so I'm going to divide in here by R squared, and I'm going to divide in here by R and multiply by that same R cubed to restore the units, to restore everything correctly, okay? So R squared over R squared, that is U squared. dr over R, that is du actually. So I'm going to pick up a U squared in here, and I'm going to pick up a du in here, and this is actually U itself, okay? Which is actually a variable that has no units. This is dimensionally used because this is meter over meter. So this is a useful transformation we were doing spherical geometry like this one. So basically what we're left with, rho naught r cubed times the integral from 0 to 1 now, because the boundaries of integration changed from basically 0 to big R now to 0 to just 1, because that's basically the new boundaries for the new variable, and it's basically 1 minus 4 over 3 u times u squared du. Does everybody's comfortable with this transformation, with this change of variables?
Yes.
Okay, so far it's simple algebra, basically at this point.
Substituting them, right? And you're gonna plug them back in at the end?
Yeah, we're gonna plug it at the end, but we have, this is a definite integral. This is not an indefinite integral. We have boundaries now, so we're gonna plug in the value. So this is a number, like 12 or 17 or 23. So whatever that number is gonna be multiplying this number, okay? So it's just a number now, because there is no other dimensions in here whatsoever. Everything is just u, and it's bounded integral from between 0 and 1. So this integral is going to be a number like 23.7 or whatever that number may be. So we're going to find it, okay? Yes, Marcela?
Yes, that makes sense.
Okay, so let's do this. It's rho naught r cubed times the integral from 0 to 1 of u squared minus 4 over 3 u cubed in du. The integral of u squared is, help, can anybody help me here? What is the integral of x squared?
1/3 x cubed.
Okay, thank you very much. Minus, first of all, 4 over 3. What is the integral of u cubed? Help.
1/4 u to the 4th.
Okay, u to the 4th over 4. Does everybody agree?
Yes. This one? 2.
Okay, between 0 and 1, cancel the 4 and the 4. Okay, so this value looks like I have, the upper limit is 1, so it's 1/3 of 1 cubed minus 1/3 of 1 to the power 4 minus 0, because the lower limit is 0 for both of them. And what is this value? 1/3 minus 1/3. What in the world is this number?
That's just 0, isn't it?
The whole thing is 0, isn't it? That's great. So Q is 0. Big fat 0. So those charges that were sprinkled in here per unit area volume, they're actually in perfect balance, because their total charge is actually equal to 0. What happened in here is, yes, we put a lot of charge in here, and it's spread throughout a bigger area in here, the positive one. But as we moved away, we took negative charges, but we have fewer of them. It's only negative 1/3 of rho naught per unit volume. But then we spread it through a bigger space in here, much bigger radius than this one's in here. So it seems like they just enough to cancel one another. So that is basically what's going on in this problem. So basically there is no charge enclosed in here. So if somebody asks you, what is the electric field outside? The electric field in this point in here, you're going to choose a Gaussian surface where R is bigger than R. You're going to choose a bigger Gaussian surface, and you're going to find that by symmetry, the electric field must be pointing this way, and the area is pointing this way, and you switch it, rotate it because of this spherical symmetry. So the electric field is the same everywhere. So on one side is going to end up basically be E times the area, which is 4 pi r squared. On the other side, it's going to be the charge enclosed divided by epsilon naught. And what is the charge enclosed inside this sphere? We just found it. So what should I plug in the numerator in here for outside of the sphere? Come on, guys. We just found the charge enclosed. This is the total charge inside the sphere. Justin, you're saying something and your microphone is off. So what should I put in the numerator in here, which is the charge enclosed? What number should I put in here?
You should put the 0, because that's what goes there.
Big fat 0. So the electric field outside is going to be 0. Thank you very much. You see that? So even if they didn't ask us that, because we calculated the total charge and we found it to be 0, so we know in this case that the electric field outside is 0. Because there is no charge enclosed. The positive charges and the negative charges are just enough to cancel one another at the end when we sum through them. Does this make sense to you guys now?
Yeah, it makes more sense now.
Yes.
Okay, very good. So the electric field outside is definitely 0. So we know that for a fact. I don't know if they ask for it or not up to this point, but if they do, we know the answer to it, okay? So that's question A. We found that charge enclosed inside, which is exactly 0 by going through this exercise of integrations and things like that. Part B. Okay, obtain an expression for the electric field in the regions B R greater than big or equal to R. And we know the answer to it for the region R greater than R. The electric field is 0 because the charge enclosed is 0. We just found it. So the answer to question B is straightforward. So imagine if this problem was out of some points and this question is out of 5 points. Just by remembering this thing, you got already credit for this question. You don't have to do anything in here. Argue by symmetry here and there and everything. So E times the integral. So it doesn't matter even if you don't have symmetry. Even if you don't have spherical symmetry. Take any arbitrary distribution. As long as it cancels inside, there is no electric field. Electric field is produced by charges. And if the charges cancel one another, then there is no electric field. You have 0 electric field. Good for this question? Question B? Okay, question C now. That's for R less than or equal to big R. Now we have to do some work here. For C, for R less than or equal to big R, we want to find the electric field. Now, if we want to find the electric field, we have to use that symmetry again. So we are in an area somewhere in here at a distance R from it. We're going to use the symmetry argument again to say that the electric field must be radial and must be the same on that surface. And the flux of the electric field on that surface, because of the spherical symmetry, is simply going to be E times 4 pi r squared because of spherical symmetry. And we made this case several times, spherical symmetry. That I think probably we just write it at this point because of the spherical symmetry. The problem states specifically that you have spherical symmetry. Actually, but spherical symmetry, that is the second basically statement that was in this problem. So that is on one side. So this is the flux of the electric field equal to the charge enclosed divided by epsilon naught. The charge enclosed. It's the same integral as we did before, except the integration is not from 0 to big R, but rather from 0 to just little r. Wherever you end up with. So I'm going to rewrite that integral here from 0 to little r and keep everything and make the change of variable in here, where this will become an r prime if you like, and take that same shape, and I have here 4 pi r prime dr, but make the same change of variable in here, and I will end up with this integral. The only difference in here is going to be an indefinite integral. That's all, because we're integrating from 0 to a little r, where r is anywhere between 0 and big R. Okay, so this integration in here, it's this result that we found, except we're not going to plug the upper limit. The lower limit, we're going to put 0 because we're summing from 0 to some r. Okay, that is less than big R. So in that case, hence in here, the upper limit is going to be basically an R value. So the upper limit is going to be actually an R over R. That is what U is. So for the second part, and we're going to use the same results. So basically, the charge enclosed is going to be rho naught times R cubed. That was part of this two terms. Times this one, plug in the value. So open parentheses, and it's going to be R cubed over R cubed. And I have a 3 in here, if you guys notice. And I have also in here R to the power 4 over 3 R to the power 4. And that's the end of it. So it's the same kind of exercise with the exception that the upper limit now is an unbounded limit. Does this step make sense to you guys? All I did is left U cubed in here and U in here to the power 4 and the same change of variable in here. Does this step make sense to you guys? This is the charge enclosed. So when we integrated through the charge, now we integrated from 0 to little r. Yes?
Yeah, that makes sense to me.
Yeah, this is only an indefinite integral. That's the only thing in here. So we're not going to get a number. We're going to get a function now. So let's do some cancellations. I have r to the power 4. Oh, did we forget about pi or something? No, we don't have any pi's in here. Oh, there was a 4 pi in here that we dropped somehow. There is a 4 pi in here. Don't forget this 4 pi. So there is a 4 pi in here. But since we were multiplying by 0, it's not going to impact the first result. But now it definitely is going to impact this the second result. So there is a 4 pi that somehow we dropped in the calculation. There's something in physics called chasing after pi. Physicists should do a lot of work, and at the end, they either have a missing pi or have an extra pi. And for this situation, we were going to actually have an extra pi, okay? Because we didn't have that one. And the physicists, what they call this step in problem solving, chasing after pi. So we fell in it in here, chasing after pi. Because usually when you solve something, you end up either with an extra one or you're short one. So in this case, we ended up with an extra one, okay? So this is a famous problem that we fall in, okay? So don't panic. So when you have a situation like this one, just go back and trace where you missed your pi. So this is a good example for that. Okay, so we had the pi that we missed, so now it cancels from here and there. And the r squared and the r cubed, no, not this r cubed, I'm sorry, this r cubed cancel, and I'm left with the 1 power in here. And this r to the power 4 drops, and I'm left with an r squared in here. Furthermore, this r to the power 4 and this r to the power 3, I'm sorry, and r to the power 3 cancel. So there is a 1 in here, r to the power 1. So let me rewrite this expression, okay, in its full glory. And I have a third that is going to come out from the two terms. So E is going to be rho naught divided by 3 epsilon naught, and I'm left with an r in here minus r squared over r. The reason why I have an r in here is because r cubed and r to the power 4, I'm left with an r in the denominator, okay? I could plug this function as a function of r, or rather, because probably they will ask me that, okay? So this is the answer to the question, is to find the function of the electric field inside. So it's not a linear as we found earlier, but this is a quadratic in R because of this term, okay? Again, we're dealing with a problem that is a non-uniform distribution. We still have about 2 minutes, so we need to finish this problem. Is it okay with you guys?
Yeah, that's fine.
Okay, because I'm borrowing from your time again. I'm sorry, probably your lunchtime and things like that. So part D is graph the electric field E as a function of little r. Again, we're going to take advantage of that u again by making this change of variables. So we're going to multiply by r and divide by r in here. And then I have in here an r squared. So instead of plotting it as a function of r, I'm going to plot it, if you guys don't mind, as a function of r over r. So I know at 1, this is exactly the circle. Okay, we are at the sphere. We are at this sphere in here. We know from part A, or part B, I guess, the electric field outside is 0. So if I'm going to draw the electric field in here, it's 0 outside. We know also if I put r equal to 0 that the electric field is 0 here too. Okay, for r equal to 0. And for r equal to big R, I will have 1 minus 1 squared, and that 2 is 0. So the electric field is 0 too. So it's a continuous function here. It's unlike the other one, which was a discrete function for the charge distribution. The electric field is continuous at that point. So let's plot this quadratic function. It's clearly quadratic function for u. So all I have to do is plot this function u minus u squared. And this function is peaked. Actually, I can take its derivative. It's 1 minus 2u equals to 0. And it's extremum, so you take the function with respect to u, and then you equate the e with respect to u, and you equate it to 0, you will find in the u that is equal to 1/2, or r, which is equal to big R over 2. So midway in here, the electric field is at its peak, okay? The reason why I know its peak is because if I take the second derivative with respect to u, of E is going to involve a negative number, -2 times the rest, okay? So it's a negative number, and the second derivative, when it's negative, in this case, it's a maximum, not a minimum. So in this case, the electric field is actually going to be a parabola. Okay, and I can find its maximum value too in here. So if it's maximum value, I can go back to this expression in here to find its maximum value. This is 1/2. This is 1/4, because 1/2 divided by 2. So 1/2 minus 1/4 is exactly 1/2. 1/4, I'm sorry. So if I plug in the expression in here, the E max is going to be equal to rho naught times R divided by 12 epsilon naught, because I will have 4 times 3, okay? So this is the maximum value of the electric field. So this is E max equals to rho naught R over 12 epsilon naught. It still has the proper dimensions, because rho naught has dimensions of charge density, which is equal to Coulomb per cubic meter. And I'm multiplying by the radius of the sphere, which is a meter. Meter and meter cancel one another. And I have the units of epsilon naught, by the way, that fix everything. So this is a Coulomb per meter squared and the units of epsilon naught. So this has the proper units of a Newton per Coulomb. Okay. So this is the maximum value of the electric field that we're going to have, and it's right smack in the middle of the sphere. So it grows from 0 quadratically and then drops back to 0 when we reach the surface of the sphere, and then stays 0 outside, because we argue that the charge is 0 inside. Okay. Question E, find the value of R at which the electric field is its maximum and find the maximum value. We already did that during the graphing stage, the previous step, because they asked us to graph this function. And when doing the graphing, because we found the maximum points, and we also found where it maxes, which is midway, which is 0.5, namely R over R is equal to to equal 1/2, namely R is equal to exactly half the radius. And we found the electric field in that point to be given by the maximum value to be just rho naught R over 12 epsilon naught. Does this problem make sense to you guys? Here is the challenge of the day. I want you to go through the very same calculations that we did for this problem, and try to think of ways to tackle problems 47 and problem 61 if they are not already part of the homework assignment. So you're going to be doing them too, but you're not going to submit them. You're not going to, you just try to tackle them and see if they make sense to you and you can handle them or not. Does this make sense to you guys?
Still processing it, but for the most part, in general, I do get it. And when I face those problems, I'll definitely look back at this video.
Okay, very good. So here's the deal. I want you guys to go through problem, what did we do? Problem 50, is it 51? 52, problem 52. This is the one that we did from top to bottom. And I was very verbose with it, trying to make the arguments left and right. I may have done probably something, especially when we were applying Gauss's law, because we did the steps before. So if those are not clear to you, please let me know. I want you to really be at ease with this problem, understanding from top to bottom, and it makes sense to you, not just do the math. It makes sense from a physical perspective, what's going on in this material, okay? Once you have that understanding, that level of understanding, look at problems 47 and problem 61 from the 15th edition, and see if you can tackle those problems too with the same level of comfort. Got it, everybody?
Yes, Professor.
Yes, Professor.
Sounds good.
Okay, very good. So we still have more problems. So we're going to meet on Thursday. What is today?
We'll meet on Thursday, yeah.
Yeah, Thursday.
Thursday we still have lecture and we still have stuff to do too. Okay, so hopefully by Thursday we'll finish this chapter. Okay. Cool. See you guys.
Did you say that you were going to extend the?
Yes. I'm going to take care of it right now. Thank you.
On the lab as well, or is that still due to?
Yes, the lab. Yes.
Okay.
Okay.
Thank you.
Professor.
I'll see you guys.
Mhm.
Thank you. Have a good day.
You too. Bye.